Chapter 1, Introduction to Simulation, Part 2. So in this part, we'll have the basic definitions. So let's start with entity. So what's entity in a simulation model? Entity could be any object or component in the system that requires explicit representation in the model. So I mean any object, anything in the system that we need to represent that thing in the simulation model explicitly, and without that, the model wouldn't be a representative of the actual system, right? So yeah, this actually shows that how we can observe the entities in the system. Usually the entities move around the system and they affect the system's state. So entities will affect the other entities' state in the system, right? So, for example, in a bank, customers are entities. They come to the bank, they move around the bank, the branch in the system, and then they stay for a while. They take the service, and then they leave the bank, right? So in a simulation model, usually we create the entities. You will see in Arena that how we do this. Entities are created and then they move around the system. They stay for a while, they take the service, and then they leave by disposing in the model. Okay. Usually entities represent real or tangible things like customers in the bank system, like parts in the simple machine processing system. Okay, and but we can have also fake entities, and we call this as modeling tricks. For example, breakdown demon or break angel. You will see again these two in Arena. That, for example, if we want to have a break in the system, in the bank, for example, half an hour as a break for the employees. So how we do this in the simulation model, we define a fake entity to make this happen. Okay, so you will see in Arena that how we do this. And yeah, in Arena we have some entities that serve other entities, like the teller, right? You see in the bank system, the teller is an entity, right? But the teller is serving other entities, the customers. So we call those entities that serve other entities as resource in Arena. Okay, so resources are the entities that serve other entities. Okay. So resources, as I said, they are entities, but they are going to serve other entities. So the entities will compete for the resources, right? So resources could be people like teller in the bank system, could be an equipment like machine in the part processing center, or it could be a space, right? So usually entities seizes a resource and then uses it for a while and then releases it after taking the service. Okay, so think of a resource being assigned to an entity rather than an entity belonging to a resource. Yeah, here none of the entities are belonging to the resources. Resources are there and they will be assigned to entities to serve them. Okay, so a resource can have several units of capacity, like seats at a table in a restaurant. If we have a restaurant and the capacity of the restaurant is our resource here, and we would like to have the status, what percent of the capacity is occupied by customers at any time. So in that case, we need to define the seats in tables at resources. And so seats at the table would be actually a unit of this resource. Okay, and identical ticketing agents at an airline counter. Okay, so And number of units of resource can be changed during simulation. Yeah, for example, if you have break time for employees, so and it would be based on a rotation mechanism. So let's say 20% of employees at any time could be on break, for example, right? So yeah, because of that, we have a variable number of, resources during the simulation. Okay. The third definition here is attributes. Attributes is defined for entities, right? So the common properties for entities are called attributes. So yeah, attributes are the common properties or features for the entities, and the specific value for the attributes will individualize the entities, right? So for example, yeah, we can say that attributes are like tags on entities. So we have tag on each entity, and but what has been written on the tag uh, depends on that specific entity, and it will individualize each specific entity from the others. Okay. For example, in the bank teller system, we have customers as entities. So the common properties for the customers could be this: bank balance, type of bank account or credit, savings, checking, and so on, right? These are the common properties for the customers in the bank system. But the specific value for the bank balance of each customer is different than the others, right? So, and these specific values will individualize the entities, okay? Or for the teller, the availability in terms of the breaks, experience that a specific teller has, and service time may vary. Yeah, service time may vary among the tellers based on their experience, right? And in machine pricing system, for the orders, or let's say for the parts or for the orders, we have time of arrival that order or the part, and due date, again for the orders or for the parts, priority among the parts or orders, and also color of the parts could be uh, uh, different among the orders. Okay, so yeah, as you see here, we defined attributes for entities. Okay, so attributes are the common properties for attributes, and the specific values for the attributes among the entities will individualize each entity from the others. Okay. Okay, so far we had all the definitions about the entities. Now think about the system, about the whole model, not just the entities. So for the whole model, we define variables. So variables are defined for the whole system, for the whole model, not just the entities. And they can be used for different kind of things like travel time between the stations. Yeah, if we have a system that a customer or an entity should travel between some stations, then the travel time is our interest to see how it varies over time, right? And then we may take an average over a period of time, then that will be our measure as a performance measure for the system, right? So yeah, here we define this as a variable. Or the number of parts in the system. Since we have parts arriving from other systems, from the external systems to our system, and it's not deterministic. I mean, it varies over time. So yeah, then we can have this variable as what's the number of parts in the system at any time, and then as I said, it varies over time, but we can again take an average over a period of time, and again that will be one measure for the performance, right? So yeah, or a simulation plug, and it's built in Arena, for example. So as you see here, the variables are not tied to entities. Yeah, as you saw, the attributes were for just entities. Okay, so yeah, they are also called local variables. We can define the attributes as local variables, but the variables in the simulation model are global. They are not local. They are not tied to just entities. They are for the whole model or the whole system. So they can be like the global variables. Okay, and and entities, but entities can change the variables. Yeah, I mean, by arriving more parts, the value of the variable is changed, right? So as you see here, entities affect the variables. So variables are based on the situation, and situation can be changed by the entities, right? As I said, the attributes were like the tag on a customer, I mean on entities. Now here we can say the variables are writing on the wall, and it's writable. It varies over time. Like let's say we have a board on the wall, and we are writing the situation of the system at any time, and it varies over time. So it looks like a tag, but not tag on entities. It's a tag on the wall for the whole system. Okay. And in Arena, we have some built-in variables, and we can use them in our simulation model. But if we need, we can define our own variables in our system. Okay. Okay. After defining the variables, we can show the system state at any time. So we define system state or state variables. So the system state is a collection of variables that contains all the information necessary to describe the system at any time. So yeah, in order to describe the system state based on our interest for the analysis of the system, then we define some variables, right? And then the collection of those variables, the values of those variables at any time will describe the system status or the system state. Okay. For example, the ith customer arrival at any time, or the teller status if it's busy or free, for example, right? So the state of the teller will vary over time. And sometimes it's he or she is busy serving the customers, or maybe sometimes he or she is free. Okay. Uh, the system state could be discrete or continuous. So based on that, we define the discrete or continuous systems. A discrete system actually is a system that the state variables change at a finite number of points in time. Okay. For example, the number of customers in the system, or the customers waiting in queue or in line. Yeah, let's consider this graph here, figure 1.1. As see here, this is for the number of customers waiting, let's say in a line. So the number of customers in the line is 1 for a while, and then at this time we have a new customer arriving to the system. So the number of customers in line will change to 2 at this point, and it will remain as 2 again for a while. And then at this time the teller, let's say, becomes free, and the teller starts serving the first customer in the line. So the number of customers in the line will drop to 1 again here at this time, and again it remains 1 for a while. And at this time again we have a new customer arriving to the system, so the number of customers in line will jump to 2 and jump to 3 at this point. So as you see here, the number of customers changes in just a discrete point of time. So let me show you here. Yeah, here there's a change, right? It increases from 1 to 2. Again, another change is here, it drops from 2 to 1. Again, it change here, it drops, it jumps from 1 to 2 and another one here. So as here, the changes in the system state is just in a discrete point of times, right? Not continuous. So this system is called a discrete system. But if the state variable changes continuously over time, then we call that system as a continuous system, like airplane speed and position. Yeah, the position of the airplane and its speed changes continuously over time. It's not discrete. And the graph for the system state could be like this. As you see here, it's changing actually continuously over time. So yeah, based on this definition, we will have two types of systems in simulation, discrete and continuous. And in this course, I mean in our course, we're going to focus on just the discrete systems, not on continuous systems. Okay. The events are instantaneous occurrences that change the state of the system. Okay, so any event is an occurrence that changes the state of the system. Okay, so they could be caused by an entity or external source. Okay, so usually they are represented by an event notice. So we'll have event notice in our simulation model for the events and with relevant information. Let's have an example here. For example, for the bank teller system, we have customer as our entity, right? So the events related to the customers are arrival and departure. So when a new customer arrives at the system, that's an event. We have the event of arrival. So any event, I mean any occurrence of this event, any arrival of a new customer will change the system status. The number of customers in the system will be increased by any arrival. And the departure of the customers, again, it's an event, and occurrence of this event again will change the system status. The number of served customers will be increased by any departure. Okay. Or for the service, we have start and completion, right? Again, start of the service and completion time of the service. These are again occurrences. We call them as events, and they will change the system status. Or for the bank, we have the closing time, for example. Right? So these are the events. So we define the events, and our approach for defining the events are the occurrences that change the system status based on our interest for a study, right? So what's activity? The time period between two associated events. So if we have two associated events and we are interested in studying the time between these two events, then we call them as activity. And usually we show these times by a statistical distribution because it's not deterministic, it's random, okay, based on the nature of the system. For example, in the bank teller system, the customer service time. So we have two events here, completion time and start time. So difference between completion time minus and service start time will be the service time, right? And usually we show the service time by a statistical distribution in our model because it's random, it's not deterministic. And or inter-arrival time. Again, we have event of arrival for the customers, right? So let's say the customer I-1 arrives at the time, and the next customer, which is the ith customer, arrives at another point in time. So the difference between the arrival time of these two customers is called customer inter-arrival time. Customer inter-arrival time. So, and that's an activity, and again we need to consider a statistical distribution for this activity in our model. Okay. Delay is entity wait time. So we can say delay is an activity, but there is no value added in this activity because we have a time period that for delay, so it looks like an activity, right? But as you saw in for activity, we have somehow value added. They actually affect directly to the system's status. But the delay is a special case of the activity that there is no value added here, and yeah, there's no value added here. So and usually in our systems in that we consider for simulation, we have waiting times, and the waiting times here are considered as delay in the simulation model. So for example, yeah, in the bank teller system, the customer wait time, so it's a delay, so it will be the difference between service start time and customer arrival time. Okay. And the clock is the variable representing simulation time. So it's a built-in variable in Arena or any simulation software. So we don't need to define this variable in our model. And event list. Event list, actually, we will in our simulation model we will have a list representing the future events. Okay, so we usually order them by the time of occurrence. Okay, so they are usually called future event list or FEL. For example, for the bank teller system, we can have this list as our FEL. Next customer arrival, okay, or current customer service completion and bank closing time. So we will have three types of events that can be occurred in future, and we have to actually order them based on their time occurrence. So this list says that the next event, from now could be an arrival and customer arrival, or it could be a current customer service completion, I mean a departure. So it could be an arrival, or it could be a departure, or it could be the bank closing time. And we should order these three events in our FEL. So based on the time occurrence, if we are going to have a new customer in future before completing the service of the current customer, then the next event would be an arrival. Or if the current customer, one of the current customers, is going to be departed before arriving a new customer, then the first event in the FEL would be departure. Okay, or maybe we're going to close the bank before any before occurrence of any of these two events, right? So yeah, so we have these three types of events, and based on their time occurrence, we order them in FEL. So we will have this FEL as the future events. Okay. So far we had the basic definitions. I mean, we have defined the basic elements of a simulation model. So in later in our course, if we are going to model a system as a simulation model, so we need to define all those elements. Okay, the entities, the events, the variables, attributes, and so on. Okay, so but that we can say that's based on a logical view. Okay, but if we consider a physical view or implementation view, we may have more elements, right? Like statistical accumulators, yeah, or arrival, departure, the end, right? So yeah, we may have more elements in our simulation model based on the approach that we have. If our approach is logical, just design a simulation model, not implementing it, then we will have the elements that we have defined so far. But if it's going to be implemented in Arena, for example, or any other softwares, then based on those softwares, we may have more elements in terms of the physical views, like statistical accumulators, arrival, departure, and the end. So you will see more in the lab sessions for these ones. Okay, so that's the part 2. And we had the basic definitions of a simulation model in part 2. We'll see more of basic concepts in the rest of in the remaining parts of this chapter. Okay, thank you.